We were talking about covariance and correlation between two random variables. Then we talked about that covariance and correlation both measure linear relationship. Now we want to look at how the concept of covariance or correlation relates to the concept of independence. Now the two things here that we should keep in mind. Number one, if two random variables x and y are independent, this means that the covariance is zero and as well as the correlation is zero. So if two random variables are independent, then the covariance or correlation would be zero. This is because independence means no relationship exists between them, whether it's linear or non-linear. So the two variables are not linearly related if they're independent. And we know when there's no linear relationship between two variables, the covariance or correlation is zero. So if two random variables are independent, because they're independent, there's no linear relationship between them. So this means the covariance or correlation is zero. Because like we talked about before, covariance and correlation measure linear relationships. So if covariance and correlation is zero, that means no linear relationship. So if two random variables are independent, they're not linearly related, and hence the covariance or correlation, which measures linear relationship, is zero. But what if we look at the other way? What if instead of looking at here, we looked at if they're independent, then their covariance is zero. But what if the covariance is zero? Can we say the two random variables are independent? Like here we said, if they're independent, then covariance is zero. But what if we look at the other way? What if covariance is zero? Then can we say the two random variables are independent? No, we cannot. Now let's look at why. Now, this is because independence is a stronger concept than covariance or correlation. This is because when we talk about independence, when we say two random variables are independent, what we're saying is there's no relationship between them, whether it's a linear or it's a non-linear relationship. Because remember when we talked about over here, if we go back a little, when we talk about the relationship between two variables, we talk about in what form are they related. This could be linear or non-linear. When we talk about independence, right, when we say two variables are independent, this means they're neither linearly related nor are they non-linearly related. But when we talk about covariance or correlation, they only measure linear relationship. They don't talk about non-linear relationship. So if we go back, so what we're saying is independence is a stronger concept. When we say two variables are independent, that means there is no linear relationship and there is no non-linear relationship either. So there is no relationship at all. But when we say covariance is zero or correlation is zero, it simply means no linear relationship because covariance and correlation only measure linear relationship. They tell us nothing about non-linear relationship. So what this means is that if the covariance or correlation is zero, we know there's no linear relationship between x and y, but the two variables may or may not be independent because there still may exist a non-linear relationship between them, which covariance cannot capture. So zero covariance simply means there's no linear relationship between them, but there may or may not be a non-linear relationship between them, and so they may or may not be independent. To be independent, they should not be a linear and they should not be a non-linear relationship. So if I know covariance is zero, I know for sure they're not linearly related, but I do not know whether they're non-linearly related or not. If they are non-linearly related, then despite the zero covariance, they will not be independent. If they're not non-linearly related, only then they'll be independent. So if covariance is zero, it only means that they're not linearly related. We do not know whether they're non-linearly related or not. So we cannot tell whether they're independent or not. Because to be independent, you should have no linear or no non-linear relationship. So in short, independence talks about linear and non-linear relationship. Independence is a stronger concept than covariance. Independence means there's no relationship, whether it's a linear or a non-linear relationship. But covariance and correlation only talk about linear relationship and not non-linear relationship, right? So when I say they're independent, that means that they're neither linearly related nor are they non-linearly related. So automatically it means covariance is zero because they're not linearly related. But covariance and correlation only talk about linear relationship. We know nothing about whether they're non-linearly related or not by just looking at covariance. So we cannot say based upon zero covariance they're independent. So independence does imply zero covariance because being independent means they're not linearly related. So so covariance is zero, where covariance measures linear relationship. But zero covariance does not necessarily imply independence because if covariance is zero, so that only means there's no linear relationship between them. Now, There could be a non-linear relationship between them, or they could be independent. That is something that the covariance in itself will not tell us. So it's important to keep in mind independence does imply zero covariance because it's a stronger concept, but zero covariance does not imply independence, because independence requires there to be no linear relationship and there to be no non-linear relationship. And covariance doesn't tell us anything about non-linear relationship. A zero covariance simply means there's no linear relationship. It may be they are independent, or it might be they're non-linearly related. So let's look at an example. Now we have a discrete random variable x with the following PMF. It takes the value 1 with probability 0.25, it takes the value 0 with probability 0.5, and it takes the value -1 with probability 0.25. Now let's look at two variables, x and x square. Now x and x square are clearly dependent, as the value of x square is decided by the value of x, right? They're clearly dependent. Right? If x is 1, then x square is also 1. If x is 0, then x square is 0. If x is -1, x square is 1. So the value of x square is decided by value of x, so they're clearly dependent. But let's look at the covariance between them. So if I want to find covariance between x and x square, so this is, if we just apply the formula, this would be expected value of x into x square, because remember covariance between x and y is expected value of xy, so here y is just x square, minus expected value of x times expected value y, and here y is just x square. So covariance between x and x square just becomes expected value of x cube minus expected value of x into expected value of x square. So we essentially just need to find the expected value of x, x square, and x cube using the PMF of x, which we know how to do. So where we know, to find expected value of a function of a discrete random variable, we just do summation over all x gx, probability x is x, and here gx is just x cube. So here to find expected value of x cube, expected value of x, expected value of x square, we just need to find the expected value of x and a function of x using the PMF of x. So expected value of x cube would just be summation over all x, x cube, probability x is x. So it's x1 cube into 0.25, like over here, plus 0 cube into 0.5, plus -1 cube into 0.25. And this turns out to be 0. Similarly, we can find expected value of x as summation over all x, x into probability x is x. So it will be 1 into 0.25 plus 0 into 0.5 plus -1 into 0.25. So this is just like finding expected value of a discrete random variable or function of a discrete random variable like x cube using the PMF of x. So from here, we can see the covariance between x and x square is just equal to 0. And the reason it's 0 is because they're not linearly related, right? You know, zero covariance measures only linear relationship. And because x and x square are not linearly related, x square is the squared value of x. It's not a linear relationship between x and x square. So naturally, the covariance will turn out to be 0, right? So the reason the covariance is 0 here, because we know x and x square do not have a linear relationship, and covariance only measures linear relationship. If there's no linear relationship, covariance will be 0. So in this example, x and x square are not independent. They're clearly dependent, even though covariance is 0. So in this example, we've shown that we have two variables, x and x square, that are not independent, even though their covariance is 0. And this is because they have a non-linear relationship, which covariance fails to capture. Zero covariance only means there's no linear relationship between them, which is true, right? So in this example, we can see that zero covariance does not necessarily imply independence. We do have zero covariance here, but they're not independent because there's a non-linear relationship between them. Right? So this example shows that zero covariance does not necessarily imply independence, as there's a non-linear relationship between the two. So independence does imply zero covariance, but zero covariance does not necessarily imply independence, as independence is a stronger concept than covariance.